Hello. Good morning to day 2 of this really exciting school. I hope you had a good evening and last evening, and we look forward to a really wonderful day ahead. So we have the third session of Friedrich now. And before we start with the presentation, please look at this. So this is part of the hands-on session for Armin's tutorial, the next tutorial. Please clone and compile this local search SAT solver and maybe be ready with the hands-on so that we can start it sort of seamlessly. Okay, with that, maybe we can switch the slides. Okay, so welcome again. And now let's get on with Friedrich 3.0.
Yeah. Okay. Good morning. Welcome back. Yesterday we left off with CGAR expansion for all exists formulas. I'll just walk through the example that I showed you yesterday again really quickly because I want to talk about an improvement of CGAR solving that I find quite interesting that uses machine learning. So remember that in this algorithm we have an abstraction that is trivially true initially, and the universal player tries to find moves, that's assignments of this set of outermost universally quantified variables in order to win the evaluation game intuitively. So in this example here, initially, our abstraction is true, trivially true, and we look for a satisfying assignment of this abstraction. So this can be any assignment of the universally quantified variables. For instance, U1 and U2. Then the existential player has to find a response that is an assignment of the existentially quantified variable E so that the combined assignment satisfies the matrix. And in this example, you can verify that playing E true will satisfy the matrix in combination with the U1, U2. So here, this clause is satisfied by U1, this one is satisfied by E, this one is satisfied by U2, and this is again satisfied by E. Okay, so sigma, the assignment where the existential player assigns E true in combination with U1, U2 satisfies the matrix, so that's a counter move for the existential player against the play of the universal player. And now we perform abstraction refinement, which means that we want to get rid of all moves for the universal player for which playing E true while the existential player is a counter move. And so we plug in this assignment sigma, for which and simplifying, we get this formula over here. And in order to make sure that future moves of the universal player will work against this move, we add the negation of this formula to the abstraction. Okay, so this here is now the new abstraction, and that's just the negation of this formula. So we go to the next iteration, find a move for the universal player that satisfies this abstraction, and one possibility is this, not U1 and not U2. Here, not E is a counter move for the existential player, and plugging in not E into the matrix, we get this formula, and abstraction refinement will add this with the negation of this to the abstraction. In the next round, we have this abstraction here, a potential move that satisfies this abstraction for the universal player is U1 and not U2. And if we plug in this universal assignment now, we can see that this formula here is unsatisfiable. So this is a winning move for the universal player against which the existential player has no counter move. And so we can just, yeah, so this SAT call here comes back unsat, and we can therefore conclude, or the algorithm concludes, that the QBF is false. Okay, so that's CGAR expansion for all exists prefixes. And we saw that or I argued that in certain cases, using this abstraction can help you get to a solution more quickly. However, there are very simple formulas where this algorithm just doesn't work well. And one example here is a formula like this, which just says, well, we have these n universally quantified variables, n existentially quantified variables, and then a matrix that just says, um, for all I, the ui variable and the ei variable have to have the same value, right? So it's like an equality on all of these uh, pairs of variables, like a bit vector equality, I guess. Okay, now let's try and figure out what the algorithm does in for this kind of example. So initially, the abstraction, trivially true, universal player will play any move. Let's say it's just setting every variable to true. Now, of course, the existential player has a response to this. It satisfies this all of these equality constraints, and that's simply to set all of their variables to true as well. So that's the response of the existential player. And now, what can we do with this, or what can refinement do here? So this move of the existential player is only a response to this move of the universal player, right? If we change any assignment or anything about the assignment of the universally quantified variables, this move now won't work because the equality E1, U1, okay, it's a bit glitchy, wouldn't be satisfied, right? So this idea that we want to get rid of multiple potential moves of the universal player doesn't really do anything here because each move of the existential player counters just one individual play of the universal player. And so refinement doesn't really achieve anything except telling us that as the universal player, we shouldn't play this again. And so by running this algorithm, we would have to go through all 2 to the n potential moves of the universal player until we can conclude that indeed this formula is true. So this is a somewhat embarrassing example for CGAR abstraction. And there's a nice solution for this that was developed a couple years ago that uses machine learning. And I think the idea is really neat. So if we just run the algorithm for a bit and observe what moves and counter moves are happening, then we can think of this as a training set to train a classifier that tells us how the existential player will respond to the universal plays. And we can do this on a variable by variable basis. So we can look at each existentially quantified variable here and try to train a classifier that tells us how the existential will respond to an individual play. So in this first example, E1 is set to true. Under this universally quantified, or in this assignment of the universally quantified variables here, it's set to false. And we can build a decision tree. We train a decision tree with a standard algorithm that will predict the moves. So from the perspective of the universal player, we now have an understanding of what the existential player will do, how they will respond to our moves, right? Yes? Oh, sorry, can you get the mic first?
So, how many regions does it need to get trained? Because it doesn't, if it needs every subset, like every yeah, then it has to go through all the 2 to the power n iterations, right?
Um,
Like,
how many training examples are needed
so
in this case?
so I mean, like,
Mhm.
why was the 2 to the power n iterations happening? So you need to have every subset of n, like one part is every possible partition of n, one part is negation, one part is not negated,
Yeah.
and you create all the 2 to the power n iterations, right? So when you're telling that you need to train the ML
Yeah.
to detect that you don't need to go through all the 2 to the power n
Mhm.
iterations, so how much of these decisions does it need to train? Like, it
Uh,
has to be much less than 2 to the power n, right?
so
So what?
good question. I'm not sure after how many examples the classifier is built. Um, it certainly is a significantly smaller number than 2 to the n. So I think here in particular, all you need to see is maybe one example where, you know, let's say for U2 here. Oh, it's work.
Maybe for each I, one negation and one.
Yeah, so maybe one negated, one unnegated.
Yeah,
Yeah, but
order of n.
so it seems to, but it seems to require just a small number of samples
Okay.
in this case. Okay.
Okay. Yeah. Thank you.
In any case, you could also, you're not guaranteed that you get just the right classifier here. Um, but what you can say as a universal player is, regardless of what what strategy the existential player here is playing, I have to have some response against it, right? So if the existential player tells me, whenever you set UI to true, I will set EI to true. As a universal player, I have to have a response against it, right? And
Okay.
if there's some mistake in the sense that the classifier doesn't pick up the right pattern, okay, then we won't get to a solution quickly, but maybe after a couple more iterations,
Okay.
we'll arrive at the right solution. Okay, in so we're trying to build this classifier, and let's assume we just get the right classifier here, which is a decision tree telling us, okay, if UI is set to true, then set EI to true. If UI is set to false, set EI to false. So yeah, so this would be this strategy. And now what we can ask, or the kind of abstraction refinement we can make now is apply now is much stronger, because instead of just saying we want to have a counter move against an individual move here of the existential player, we can refine with an entire strategy, right? With a function. We can say we want to make sure that if the strategy that the existential player is playing is set EI to UI, then we have to have a response against it. And so we can refine this abstraction and add the strategy here and require that even if the strategy is played by the existential player, as the universal player, we have to have a chance to make the matrix false, right? We have to pick an assignment of the universally quantified variables that works against this strategy. But in this example, if we just can just check syntactically that if we have this here and the negation of phi, then, well, phi is just a strategy here itself, right? So in this case, the strategy played by or the encoding of the strategy, rather, played by the existential player is precisely the matrix. So so this formula here will be unsatisfiable. And so the abstraction will become unsatisfiable after adding the strategy here. Yeah.
I mean, if we could learn the strategy, then any problem can be solved, right? I can, I mean, what is so special about this kind of, I mean, for what kind of problems would this work? And
Ooh, for what kind of problems would this work? Eh, I don't think we have a systematic understanding, but um,
I mean,
here, even if, yeah.
you're learning Skolem functions here,
Mhm.
right?
Yes, but you don't have to learn the Skolem functions. Like, even if the Skolem function doesn't exist, you're trying have a better kind of abstraction refinement as a universal player.
Yeah, I thought the
Yeah.
whole purpose of the abstraction
Mhm.
refinement was to arrive at the right set or
Sorry, come again?
to arrive at you know to zoom down onto what assignments the universal player can play for which the previous assignments work, right? And here you're trying to express it in a functional way rather than
Yeah.
having specific assignments for the existential player. So I'm just wondering, I mean, does this not, I mean, if this could really work well in all instances, it would obviate the problem. It would obviate the need for other things, right?
You mean if we can build a classifier, then yeah, then we don't have to
I mean,
do anything
this
beyond
is
that.
extremely effective.
Hmm?
I know that, and this has been used subsequently.
I think it's not always effective. There are examples where it doesn't help,
Oh, is it?
but yeah. But so we've noticed in certain benchmarks that turning this kind of abstraction, refinement, and the learning off even helps. If there's no clear pattern to the existential strategies, then it can just maintaining the plays, training the classifier apparently just um, yeah, it gives you a performance hit, and it doesn't really help in certain cases. So I mean, in this example, it's a little maybe a bit misleading because here immediately you learn the right strategy and then you're done, right?
There's an alternative approach of doing abstraction refinement for which this example just goes through very
Yeah.
nicely.
So this is just one example that this approach can deal with well. Um, I'm sure there are others. I don't have a more, I have to admit, I don't have a more complicated example that shows what happens if you. So I think what could happen is that you need multiple strategies and then um, or you train multiple times, and then maybe you don't. Again, if it's an unsatisfiable instance, it's a bit unclear because you don't have an existential winning strategy, right? So, right, maybe we have it on.
Like one special case could be that for, let's say, one of the UIs, it is not equivalent to EI, but for all others it is. Let's say for U2 it is negation of EI, but for every other case UI is equivalent to EI. Now a machine learning approach will actually very easily converge to this pattern, saying that for every UI this is equivalent. But because there are these small partitions, these small cases where it doesn't work, you will need to really zero down to that particular example to be able to learn that, I would say, complex function.
I think that's what could be happening here. That right, you have uh, you pick up on the part that's easy to predict,
Right.
and then you work on that. But I have to admit, I don't have a good intuitive understanding of how this plays out on different examples.
This isn't really a complete approach, right? You could end up blocking potentially good universal moves by this, like what. So let's say you learn something,
Mhm.
and you could end up blocking moves that you haven't tried yet, right?
Um, so the question is this complete? Can you make a
Mhm.
mistake there in some sense? I think it should work in any case because even if it's not the right strategy,
Mhm.
whatever the existential sort of promises to play, as the universal player, I better have to have some answer against it, right? So even if I have multiple strategies accumulating there,
Mhm.
I need to still be able to play effectively against them, right? So I think this.
Like, is it not possible that, let's say, in the space of the moves of the universal player, there's just one move that works, but you haven't tried that one, you've tried others, and those end up blocking this one special move that works? Was this abstraction somehow dictates like the space of future moves, let's
Mhm.
say, and now the that one special move has been blocked by whatever patterns you saw and whatever the machine learning model learned from these patterns.
No, it shouldn't block moves entirely. Just should what you're getting as a solution of the abstraction is a move that works against all the strategies that end up being in this
Okay.
abstraction. And regardless of what options the existential is giving you here of how they can play, you need to have a response to that. Of course, that kind of needs a more formal argument for why this really works, but that's my intuition that you can't really make a mistake here, because even if the existential strategy is something weird, or there are multiple weird strategies, you still, as the universal player, you need to be able to deal with them.
Yeah. So
But
like
yeah, we can.
the definition of, so the abstraction isn't directly dictating the universal moves, but it's rather specifying the space of like the existential moves that the universal player needs to counteract.
Exactly, yes,
Okay.
that's the
Yeah. Fair
the
enough.
moves they have to be able to counter. Mhm.
Thanks.
Okay, so in one thing I should mention here is that, of course, in this case, it's very easy to get a propositional encoding of our classifier. In general, you have to have may need to introduce auxiliary variables to, or well, you don't have to, but you just have to encode the decision tree representing the strategy, and you could run this kind of approach, I suppose, with any classifier that you can effectively translate into propositional logic and add to a SAT instance here. Okay, so here in just one move, or well, after adding the strategy to the abstraction, if it's the right strategy, then we can immediately conclude that this formula is true because the abstraction becomes unsatisfiable. So there are multiple extensions of this algorithm for two quantifier blocks. You can have a version of this that works for arbitrary quantifier prefixes. There's a recursive algorithm. There is also a non-recursive version of CGAR, where I think the correspondence with the underlying proof system is more clearly visible. And then there's quite a bit of work in QBF proof complexity on the underlying proof system, and comparing that with Q resolution, which is the underlying proof system of quantified CDCL. So in particular, there are exponential separations both ways, right? So there are classes of formulas where Q resolution quantified CDCL does much better than CGAR expansion. There are classes where CGAR expansion is a lot better. What's interesting is that if you have a constant number of quantifier alternations, if you have a constant number of quantifier alternations, then in principle, CGAR expansion is no worse, or shouldn't be worse in a proof theoretic sense than quantified CDCL. So there you have a polynomial simulation of for all x plus res. Q resolution is polynomially simulated by for all x plus res for such classes of formulas, and that was a nice result, I think, because experimentally you can often observe that CGAR expansion does well when you have few quantifier alternations, maybe two or three, or one or two. All right, so there's another way of performing CGAR expansion that's called clause selection. And the idea here is that we number our clauses. So in this example, we have 3 clauses. And we can think of the moves of the universal player. Okay, maybe. So think about the CGAR abstraction. Well, the CGAR algorithm running on this example, right? Initially, a move by the universal player might be to play not x, not x1, not x2 here. If we plug that assignment into our formula or matrix, we end up with these 2 clauses here, right? So this one is satisfied, and here we remove the x2 literal, And well, this one remains unchanged. And so in a sense, we can think of the universal player selecting a subset of clauses restricted to the existentially quantified variables that the existential player has to still satisfy, right? So in this case, with this assignment, the universal player selects clauses 2 and 3. And the existential player now, well, has to respond in a way where they can satisfy all of the clauses that are selected. Now, and for the abstraction refinement, selecting a certain subset of clauses did not really work out for the universal player if the existential player has a counter move. And therefore, the abstraction refinement has to ensure that the universal player in their next iteration will select at least one of the clauses that were not selected in this iteration. And so we get a different kind or flavor of CGAR, where instead of working directly with the matrix for the refinements, we use variables representing which clauses are selected. And this was introduced independently by 2 groups of researchers a few years ago. So this looks a bit complicated, but all it says is the abstraction here initially is the abstraction now only speaks, or we want to only get values of certain selection variables that represents which clauses are selected. And the only constraint we have on that is that if we assign a selection variable true, or if we assign a selection variable true, if we select a certain clause, the universal part of that clause has to be falsified, right? So that the set of selections we make really corresponds to an assignment of the universally quantified variables. That's what this says. If we assign a selection variable true, then each literal of this clause has to be false. And now we, again, run a loop where we solve the abstraction, or try to solve the abstraction. If the abstraction is unsatisfiable, then no moves are remaining for the universal player and the existential player wins. Otherwise, we take a look at the clauses that are selected. So that's just the set of clauses for which their selection variables are true. And we restrict the matrix to these clauses and to the existentially quantified variables, right? So that's what we did on the previous slide. In the example, you just remove the universally quantified literals, and that's the formula that you get from selecting these variables for the existential player. And now the existential player has to satisfy this formula. If there's no counter move for them, they lose. So the QBF is false. And otherwise, we refine the abstraction. And what's nice about this approach is that the refinement will now always be causal. So we look at the set of clauses that are, so the set of clauses that are satisfied by the assignment of the existential player. And then we say, okay, we've refined the abstraction by requiring that in the next iteration, we have to select one clause that wasn't satisfied by the existential player. Because, of course, if we only select variables that they could simultaneously, or select clauses that the existential player could simultaneously satisfy, then again, the existential player will win. So the refinement step says, well, I have to pick a clause by suitably assigning or picking selection variables. Well, I have to select a clause that the existential didn't satisfy in the previous move. So here's a quick example. That's our QBF. We introduce selection variables for each clause, so S1 to S4, and solve the initially empty abstraction. Well, sorry, it's not empty. It just requires that our choice of selection variables, or the choice of the assignment of selection variables, is consistent with some assignment of the universal variables. So here, if we set U1 false, U2 true, then indeed we can select this clause. We can select this one. We can select this one as well. And then again, we cannot select this one. Okay, so in this case, we can set S1 as 3 to true. And notice that by this initial abstraction, we're not required to choose exactly the clauses that are not satisfied by this universal assignment. We could choose fewer of them. The only constraint is that if we select a clause, it has to be non-satisfied. Okay, the counter move, or a counter move for the existential player, is playing E1, E2 true. And that will satisfy clauses C1, C2, C3. Yep. And so in our abstraction refinement step, we have to say, okay, well, you have to pick clause 4, because all the others can be simultaneously satisfied by the existential player. And then in the second iteration, we may solve the abstraction and get this solution here, which selects clauses 1, 2, and 4. And then we get this restriction of the matrix for the existential player, and that is unsatisfiable, right? That has a short resolution refutation. Answer.
So I guess for the move of the existential player, like to satisfy the clauses that are selected by the universal player,
They have to, yeah.
and also as many of the other clauses as possible, right? That we prefer. Is it some kind of a max SAT problem or something?
Indeed, you could probably gain something from trying to satisfy as many clauses as possible. Now, from the top of my head, I don't know whether that's been done already or not. I can imagine that if you of course have many of these calls. So
If I formulate it as a max SAT.
yeah,
So then, I mean, these would be the hard clauses and the.
Indeed, you could use maxset for this. My suspicion is that it's maybe a bit overkill to do that, because calling the SAT solver is fairly cheap. For a maxset, maybe it doesn't pay off to find a kind of an optimal counterplay in this case. But I don't know. It's possible that this has been attempted already. Certainly an option. My suspicion is that maybe it'll be too costly to do that in each iteration.
I think for the 2 QBF case, this has been done. I mean, we did it.
Oh, okay. Oh, yeah.
Just
Okay.
in
I see. That's why you asked this question. Okay, then. Sorry, I'm not aware of this.
happens with more alternations, whether it complicates.
Okay. Yeah. I also stick to one alternation here, because that's kind of easy enough to understand.
In the standard cigar case, you have to, well, create a CNF out of your, once you have a strategy or an assignment for the existential. But that CNF is going to create precisely those variables that you have here, right? Whenever you enter an existential move, you're going to get, well, some of these variables. So is the main difference that you're only doing it once and that you're basically reusing your structure here? Or is there something else going on?
It's a good question. Why this really ends up being different from the standard Seeger thing. So there's kind of a proof theoretic argument that these things have to be different, but honestly, I don't have a good intuition for why that's the case. So apparently this ends up being, or the proof system for this, for unsatisfiable formulas, ends up being level-ordered Q resolution, so a very restricted form of Q resolution. And we know that Seeger expansion is stronger than that on, well, I know is it unconditionally stronger, but certainly there are classes of formulas where this is, where Seeger expansion in the, as in the previous version or the first version is stronger than this. In practice, this seems to perform better for, in many cases. But so my honest answer is right now I can't really point to a good reason why this ends up being really different. Maybe we need more quantum. Well, no, I think it should even make a difference here. But I'm afraid I don't have a good explanation for that. Yeah.
Thank you.
Yeah, so this was for clause selection for one quantifier alternation. You can generalize this to arbitrary quantifier prefixes. And you get, so this was for prenex. Okay, sorry, no. Of course, you can generalize it to arbitrary quantifier prefixes, but even beyond conjunctive normal form. So there are versions of this that work on, so one version that works on prenex QBF, and even, oh, I'm missing this. Okay, so there's even a version, I think, that works on not necessarily prenex formula. So the kind of QBF, the most general form that we introduced syntactically at the beginning. And then there's quite a bit of work again in the QBF proof complexity work on this, or well, no, actually there's only one paper in this case, which shows that this is equivalent to a restricted form of Q resolution. Okay. In the remaining time, I'd like to talk about another algorithm, which now is really specific to for all exists to QBF, which is an important case in practice. And that algorithm is called incremental determinization. Again, the motivating example here for this is this formula that says for all U1, for all until for all UN, there exists existentially quantified, well, there exists E1 to En so that UI and EI are equivalent. Here it's just written as a ZNF formula, right? So this just says UI and EI have to have the same value. And what you can observe here is that just these constraints by themselves, if you look at them, they immediately give you the right strategy for the existential player. So this is for variable EI, these two clauses amount to an exhaustive case distinction. So there are really only two cases. UI is false, then EI has to be false, and if UI is true, then EI has to be true, right? And so these two clauses we can read as implications. One where that says if UI is false, EI has to be false, and if UI has to be true, EI has to be true. So that's what we get for this very simple example. But in a more general setting, for some existentially quantified variable E, we may interpret the clauses that it occurs in as implications, right? So if we have a clause C1 or not E, then we can read this as an implication, not C1 implies not E. So we can look at all the clauses that E occurs in, and I should add here, some of these occurrences might be negated, right? And then we're going to say the variable E is deterministic if the propositional formula consisting just of the clause parts without E is unsatisfiable. And what that means is that the these clauses here, read as implications, are an exhaustive case distinction. So if at least one of these clauses is always falsified by an assignment, and that's what it means for this to be unsatisfiable, then one of these cases here, one of these implications applies, right? So or the other way around, in case this is satisfiable, then it is possible that none of these rules or implications read as rules fires. But if it's unsatisfiable, one of these cases will apply. And then if the variable is deterministic, we may actually have a situation where we have two clauses, two implications of this form that could apply at the same time and that are contradicting, right? So here we may have two clauses that one forcing E to true, the other forcing E to false, so that both not Ci and not Cj could be true at the same time. And then we're going to say that the variable is conflicted. Now, the underlying idea or the underlying aspiration of incremental determinization is to lift the CDC algorithm from SAT to quantified Boolean formulas and to lift it to the level of strategies. So in CDCL, we have a trail consisting of a variable assignment. And in incremental determinization, as we'll see, the trail consists essentially or represents a partial strategy for the existential player. In CDCL, propagation means unit propagation, applying the unit clause rule. In incremental determinization, the analog of propagation is finding unique strategy functions, finding variables that are deterministic, that are determined, and not conflicted. Decisions in CDL correspond to setting a variable to a certain value. In incremental determinization, decisions are made by adding clauses that ensure that a variable is deterministic. And finally, not finally, we have a conflict in CDCL if we find under some partial assignment two unit clauses that contain opposing literals. And in incremental determinization, it's this case where we have a conflicted existential variable. And then finally, in CDCL, learning means learning a clause. And as we will see, in incremental determinization, we can use the same kind of learning technique to derive new clauses. Okay, so this goes back to a paper by Markus Rabe and Sanchit Seshia from 2016. So let's look at the propagation routine in a bit more detail. Okay, so here we have two arguments, which are just the prefix, and D will be a set of variables that have previously been identified as deterministic. And now we want to look for existentially quantified variables that are not already in D and that are unique consequences. And what I mean by that is that you have some clauses in your formula that contain E or not E, and all of the other variables in these clauses are variables that are already identified as deterministic or that are universally quantified variables. Right? But it's not required that all clauses in which E occurs have that property, but if you have some of them, then at least you have a reason to look at this variable and figure out whether it's deterministic. Now, as long as you have as long as you have such variables, you'll take some such variable and you decide whether it's deterministic, right? So we had that on the previous slide. You just look at all the clauses that it occurs in, remove E from that clause, and then you ask, are all these clauses simultaneously satisfied, right? In that case, if it's unsatisfiable, it's deterministic. If it's satisfiable, it's not deterministic. And once you have found a variable that's deterministic, you ask, oh, okay, is it conflicted? If it is conflicted, we'll find an assignment of the universally quantified variables and of the variables that have already been identified as deterministic, and return that as our result. If the variable is not conflicted, well, then the set of clauses that it occurs in, where it is a unique consequence, we can interpret as a definition of the Skolem function, the strategy function for E. And so we can just say, oh, now E is deterministic, and it's fine. So we have a strategy for this variable, a strategy function for this variable. So let's run through an example here. We only have one universally quantified variable and three existentially quantified variables here. And these are our clauses. Okay, let's look at the candidates here where a variable is a unique consequence in the first iteration. So here in this first clause, E1 is contained, U is contained, and so E1 is a unique consequence because U we treat as, so E1 is the only existential variable here. Similarly here, for this clause, this is not the case for E2 or E1 for that matter. And here, here actually E2 would be a candidate. And then in these two clauses, these two clauses don't give us candidates. So here I actually made a mistake. I think this should be E1, E2. We could look at E2 here as well because we have this clause. But let's assume we go for E1 first. Okay, so D is empty initially. And let's suppose we look at E1 here. And so our E here is E1. Is this deterministic? Well, given these two clauses, yes, it's deterministic. So this just requires us to, it's deterministic and it's not conflicted, right? So the function here for E1 is E1 not equal to U. Okay, in the second iteration, what are the clauses where an existentially quantified variable is a unique consequence? Well, now here for this clause, E1 is in D, and E2 is not in D. So here E2 is a unique consequence. Here E2 is also still a unique consequence. And here actually E3 is a unique consequence. So unfortunately I made another mistake here. E3 should be in the set as well, right? But let's assume we're looking at, or we're picking E2 here. Then we have these two clauses. And just on its own, okay, if we look at the SAT call for determinicity, we're asking, is E1 and U, is that satisfiable? Yes, that would be satisfiable on its own. So in that sense, the variable would not be deterministic. But then we can ask, is it deterministic in combination with the strategy we already have for E1? And because E1 is set to not U, in combination with these two clauses that specify the function for E1, the determinicity call, which says E1 and U will be unsatisfiable, right? Because this here becomes not U, and not U and U is unsatisfiable. So here, after fixing that first function or adding this to our set of deterministic variables, E2 now becomes deterministic as well. And in the paper, there's a distinction here between local determinicity, which is ignoring the other scaling functions. Now, if you have local determinicity, then this is a slightly simpler SAT call in many cases. And if that already gives you determinicity, you're fine. But if that doesn't tell you that your variable is deterministic, you'll have this or use this stronger criteria. Well, yeah, the stronger criterion here, or the more specific criterion, and ask, is it deterministic in combination with the clauses that I already have for the other variables. Okay, and then finally, last iteration, we look at E3. Now we have two clauses here where E3 is a unique consequence. It's this one, and this one. And here we can verify that E3 is actually conflicted, because this assignment here, not U, not E2, and E1, is consistent with the strategy functions that we have for variables E1, E2. So here, E1 we already said is equivalent to not U, so that's fine. And then if E1, no, sorry, what? Yes, well, if U is false, then E2 has to be false, right? So we have these two clauses where E2 is a unique consequence, or where E2 was a unique consequence in the previous iteration. These define the function for E2. And in case U is false, E2 has to be false as well. Okay. So here we have a conflict for E3, and the algorithm, the propagation routine, will return E3 along with that conflicting assignment. We'll get to how that kind of conflict is analyzed in the next slide. Before that, we have to talk about decisions in this algorithm. So let's look at this example here. Oh yeah, so here's one clause where E1 is a unique consequence. So if we use our, oh sorry, yeah, question?
In the previous slide, I was wondering if, is it at all the case that the order in which we are looking at the variables will matter? Because in some sense, we're expressing the strategy of one of the EIs with respect to the other one, right?
Yes, so I think you might get different strategies depending on the order in which you choose the variables. I'm honestly not completely sure now. I don't want to go on record saying anything. I mean, in SAT, if you don't have a conflict, then there's a unique assignment you get by propagation here. Oh, I am not sure. Good question. Could be, yeah, okay. Yeah.
You're just getting through propagation and
Yeah, I'm willing to believe that's the case. Yeah, but I'm not entirely sure whether it could make a difference just for, certainly, which functions you express in terms of which variables will change. So just syntactically, they're going to be different functions, right? So therefore,
once you start adding the extra clauses which start determinizing, then of course it will everything prior to that before added the first determinizing sequence of the original form.
So certainly, yes. If you haven't made any decisions yet, as if you haven't added any additional clauses, then everything you derive comes from the original formula, and so it's sound in that sense. But the functions you will get, just in terms of the implications, will be different, right? Depending on the order in which you propagate, right? Because if you propagate E1 first, you get a function for E1 maybe just in terms of U, and then a function for E2 that also uses U1. Whereas if you go the other way, you get a function for E2 just in terms of U.
The function for E2 in terms of E1
Yeah.
can be expressed also in terms of U by substituting the function for E.
Yes, it can be expressed that way. Will that, after substitution, will all the functions be the same?
Before the first decision, they're all.
Okay. Well, yeah. Okay, I'm happy to believe that. I would like for that to be the case. I just, yeah, I think I need to see a proof to really convince myself that's the case. Excellent question. So back to decisions. So here for variable E1, we just have this clause where it occurs as a unique consequence. And this by itself is satisfiable. So E1 is not deterministic in this initial iteration. And for E2, we have, well, sorry, I think I made a mistake here because this clause is also one where E2 occurs as a unique consequence. But let's just assume, no, wait. That's the clause. Okay, well, in any case, let's assume that the variable is not deterministic. What we want to do is make the variable deterministic by adding new constraints. And the idea is we want to express that unless E2 is implied by the clauses where E2 is a unique consequence, then if not E2 is not implied, we want to set E2 to true. So in this case, well, the important thing is the general case is this, right? We look at all the clauses where not E is a unique consequence. And if none of these, or not E is a unique consequence, if none of these rules apply, if we're not forced to set E to false, we're going to set E to true. Now, this in general won't be a CNF formula, but we can convert it to CNF, and that's all we need. We need to make sure that we have a function for E2, and yeah, we can add auxiliary variables to make sure that we add this constraint to our SAT solver. Okay, now we know how decisions work. We add auxiliary clauses. We know how propagation works. What if propagation gives us a conflict? Then we have an assignment of the universally quantified variables and a partial strategy, which consists of, it consists of all clauses where variables are unique or were unique consequences, all variables in D, plus potentially some of these constraints we added for decisions. But we have a partial strategy for the variables that are in D. And so given this partial strategy, there's a unique assignment that the strategy will give us for the variables in D, given the assignment tau of the universally quantified variables. The joint assignment will satisfy our encoding of the strategy, right? It's consistent with the strategy. but it falsifies the formula, or maybe the assignment or the formula becomes unsatisfiable under this assignment. Maybe it's not immediately falsified. But in any case, we just have an assignment of the universal variables and the existential variables that have been made deterministic or that are deterministic, that is the cause for a problem. And then the idea is to simply use that partial assignment and perform conflict analysis as it is done in CDCL. So the deterministic variables will treat as if they'd been propagated by unit propagation. And well, the decision variables, or the variables where we added clauses to make them deterministic, we will treat as decision variables in CDCL. And finally, the universal variables will well, treat as having been assigned at decision level 0. Right? So these will be kind of the initial part of our CDCL trail. Now, how can we perform conflict analysis? So let's assume this is essentially the example from before, except there's one clause missing that we're now adding as a decision. So E1, let me just make sure that's really the case. E1 initially is not deterministic, and in fact, there is no variable here that's deterministic. So suppose we make E1 deterministic by adding a clause which says, okay, well, if U is false, then E1 has to be true. Now, in this very simple example, we can just add a clause to make E1 deterministic. Well, in general, that's not the case, but in this example, we can add a clause to make it deterministic. So that's we'll call that a decision clause or decision constraint. And so now we're increasing the decision level in our algorithm, just like in CDCL. So everything that's happening now is at decision level 1 because we've made E1 deterministic by adding a clause. We've made a decision. And now we propagate again. So here's the pseudocode for the propagation routine. Now, okay, E1 is deterministic, of course. In the next iteration, okay, we have these two clauses, which we already saw in the previous example, make E2 deterministic as well. And then finally, E3 is deterministic, but it's also conflicted. Okay, so that's the assignment under which E3 is conflicted. And in fact, to have a unique conflict clause, we can now maybe add the assignment E3 here so that we have one clause in the matrix that's falsified. So it's either going to be, from this partial assignment, either this or this clause would be falsified. Let's just make sure that it's this one, okay? Now we can perform conflict analysis as in CDCL. And so starting from the conflict clause, we look at the last variable that was assigned here, that is E3. Okay, that's actually, I think. So we have this. We have these two clauses that would propagate E3 in different polarities, right? So we take one and resolve it with the other. That's our initial step. And then we get this clause here. Now the last clause that was propagated, or the last variable that was propagated is E2. Because E2 is not a decision, its strategy function is defined just by the clauses, right? Just by the clauses where it is a unique consequence. So we can figure out that or we can determine a clause which would cause propagation of E2 under a partial assignment of the remaining variables, and that's this clause here, right? This is one where E2 is a unique consequence, And we can resolve our current clause with this clause to derive a new clause. And now, if we assume that U is assigned at decision level 0, this is actually an asserting clause in the CDCL sense, right? Because E1 was assigned at decision level 0. So there's a unique variable that's assigned at the highest decision level. And therefore, we can stop our conflict analysis. And this will be our learn clause. Okay. Great. So we add this clause, we go back to decision level 0, and we start propagating again. Okay, now we can actually run the remaining algorithm, which is full incremental determinization. Now, the simplified pseudocode looks a lot like CDCL. We propagate. If there's a conflict, we perform conflict analysis. We add a new clause. We backtrack. If the clause only contains universally quantified variables, then we say, okay, in that case, the formula is false. So notice that we've only used resolution to derive learned clauses. So whatever clause we add is, or adding whichever clause we derived is sound. And if we have a clause that only contains universally quantified variables, we already argued yesterday, then the formula is unsatisfiable. So if the clause is not purely universal, we just add it to our set of clauses. We backtrack to the right decision level. Otherwise, if we don't have a conflict, we ask, have all variables been made deterministic without reaching a conflict? If that's the case, our partial model is in fact a model, and we can say that the QBF is true. If not all variables have been made deterministic, well, then there is one that's not deterministic, that doesn't have a strategy function yet, and so we make it deterministic by adding this decision constraint. Okay, so let's run through the full example. So this is the same formula we had on the previous slide. We already saw what happens if we make E1 deterministic. So we add this decision clause here. And then through the conflict analysis process from the previous slide, we add a new clause, U, not E1 instead, that's derived as a learn clause, which is part of our database. And we backtrack to decision level 0. Now again, we propagate. Here, E1 is a unique consequence in both of these clauses. And in both cases, well, and this is actually a set of clauses that makes E1 deterministic, right? And in both cases, E1 is assigned false. So we get the constant function E1 false for this variable. Okay. Now, in the second iteration, we have E2 as a unique consequence in these two clauses here. And now if we just look at, okay, we have E1 and U, that's our determinicity check. On its own, this would be satisfiable, but now in combination with not E1, this will be unsatisfiable, right? Because we have E1 here in conjunction with our previous, well, the function for E1, this will become unsatisfiable. And so variable E2 is deterministic. But it's also conflicted, right? If we plug in E1 here, so already E1 is a constant function, so E2 has to be true. But if we assign U false, then E2 has to be false as well, right? So this variable E2 is conflicted now. This is unsatisfiable. and E2 is conflicted under this assignment, which is consistent with our strategy for E1. And so we can perform conflict analysis, starting from these two clauses, resolve them to get U or E1, resolve that with this clause here, and now we've derived a purely universal clause and can therefore conclude that this QBF is unsatisfiable. Okay, or the 2QBF in this case is false. Okay, that's the algorithm. There's been some work on extending this. It can be used for Boolean functional synthesis, which means that even if the 2QBF is not true, even if you don't have a strategy that works against every assignment of the universal variables, you may want to get functions that work whenever there is a response for the existential player against a particular assignment of the universal variables. That's Boolean functional synthesis. And you can combine incremental determinization with some form of Seeger and get an improvement in certain cases as well. Just briefly want to add a disclaimer here that there are many other topics on QBF that I didn't talk about. So typically, if you have a QBF solver, you want to pre-process your instance. So there's a lot of work on lifting techniques from SAT to QBF as far as pre-processing is concerned. So there's, you can apply this causal pre-processing that's done in SAT. In some sense, also reconstructing a circuit is a form of pre-processing that one can look into. There are more QBF solvers one could talk about. So there are symbolic solvers that use BDDs or some other similar representation. You can extend QCDCL by, at certain points in your CDCL search, calling maybe an expansion solver and try to work with more general axioms in the sense. And then, well, QBF solvers in many applications shouldn't just return true or false. You'd want the strategies. And okay, so first of all, they should output a proof that you can verify. And so there's been some work on certification and a lot of work on proof complexity, comparing different proof systems underlying solvers. And then in many cases, you'd like to also get a strategy out of your solver. And one way of doing this is through the proof in a process called strategy extraction. Yeah, these are some further topics I can think of. So that's the end of my talk. I hope I convinced you that there's quite a bit of room for experimentation in QBF. So unlike in SAT, where I think you really need to tune your solver quite a bit to have any chance to get an improvement, in QBF, that's a little easier if you have the right idea. And I think it's also fair to say that we haven't found the CDCL analog for QBF yet, in the sense that it's this one algorithm that works very well on a broad range of instances of practical relevance. Maybe, this is a bit of a chicken and egg problem, but at the same time, we haven't found the killer application yet that QBF is really well suited for, or the solvers that we have are really suited for, and that in turn let us improve our solvers to work even better on that application. Yeah, and overall, I think there's much to do, both on the theory side and as far as solver development is concerned. So I hope I maybe have piqued your interest, and I can get some of you to consider contributing to this area. Thank you very much.
Thank you, Pradesh, for an amazing tutorial. And the timing is it's exactly 10:15.
Oh, great.
Couldn't get better. So we have a small event for you.
Oh, excellent. Mhm.
So you have to take it out and
Mhm.
to us it's not empty.
Yeah. It's a nice box. Oh, does it open here?
Yeah, you can shoot it.
Oh, yeah. Yeah. Yeah, there you go. Yeah. Oh, oh.
Pose for photographs as well.
Oh, an elephant. Thank you. Thank you very much.
Thank you so much for the amazing talk. So we can break for coffee and we come back in another half an hour for Armin's. Oh, it's 15 minutes. Okay,
Yeah,
sorry.
yeah.
15
Thank you.
minutes. Okay. So, okay, we have short presentations after this. Yes, okay.
Yeah.
So,
Hi. Just a small announcement, by the way. The people who are going to be giving the short presentations, I require them to like stay up for a few minutes, like stay in for a few minutes. We just want to set things up. So that is um, Arijit Shaw is here. Yeah. And then Nitesh Trivedi, Aditya Patil. Okay. And SK Asif Kumar. Yeah. So we just require you guys to stay in for a few minutes.
चाहेगा हेलो हेलो माइक टेस्टिंग 1 2 3 बहुत कम है आवाज हाँ और कुछ माइक टेस्टिंग 1 2 3 हेलो ठीक है वो वाला चेक कर लेते हैं मैं बढ़ा दूंगा थोड़ा सा और इंक्रीज करूंगा और वो
ये क्या? I didn't stop this.
Test 1 2 3. Test 1 2 3. Check. Test 1 2 3. Check. Test 1 2 3.